So we used the LASA.
Results from binding energy studies in the context of nuclear astrophysics. And we have heard a lot so far about nuclear reactions. So this will be something a bit different now, because we will really focus on ground state properties of nuclei and low energy, actually, nuclear physics. So this will be the outline of my talk. A brief introduction on the place and technique we use to perform those measurements. And then I will highlight two mass measurement campaigns that took place during my PhD at the ISOL Trap mass spectrometer at CERN, and also an analysis that I performed during my postdoc there, and a few projects related to nuclear astrophysics in the new place I am working since September, which is the University of Uvascular and ISOL group. So a few words of introduction. First of all, as well everywhere, if we want to study radioactive ion beams, we need to produce them. And the facility, or one of the pioneering facility for low energy nuclear physics in the production of radioactive ion beams has been the ISOL facility. It is the actually longest experiment facility still at CERN. Right, the Memorandum of Understanding was signed in 1964, and the first beams were delivered to users there in 1967. So we were celebrating in 2017 more than 50 years of actual physics at ISOL at CERN. Okay, so this is an overview of the CERN Accelerator Complex, and ISOL is actually the only facility taking its primary beam, which in our case is protons, from the PSB, the proton synchrotron booster. Okay, and it's important to note that actually we are actually getting and guaranteed more than 50% of all the protons that are produced at CERN are actually used at ISOL to do nuclear experiments. Okay, so I will be talking about mass measurement. The ISOL hall is a very crowded place, beautiful but very crowded. So I was mentioning this is the target area where the incoming beam can be impinged on two targets. Each of the target station have its own mass separator to perform an isobaric separation, and to select rather the isobar of interest. And then in the very sprawling, I would say, layout of the lab, the ISOL Trap mass spectrometer is located at the very end of the main beam line. There. So what tools do we use to actually measure masses with high precision, where in our case, we are actually using a penning trap, which is actually not much bigger or much larger than my fist. So it's a rather small device. And the idea is to measure in this trap the free cyclotron frequency of the ions that we want to study. The idea is that because of the presence of confining E field, which confines the ion axially, and together with a strong magnetic field, which is applied axially, which provides the axial confinement, the free cyclotron motion of the ions that we would get if only the B field was present is slightly modified. However, by performing a resonant measurement, we can actually get back to this frequency, and it is actually directly inverse proportional to the mass of the ions that we want to study. So measuring in this device allows us to directly have access to the mass of our ion of interest. It's worth noted that at ISOL, the beam is produced at 60 kilo electron volt, and the penning trap operates, I think the trapping potential is on the order of 10 eV right here. So when I'm talking about low energy nuclear physics, you can imagine the different steps, and I will go through them after, that are required to slow down that beam, purify that beam, and go from 60 kilo electron volts to the few tens of EV that are required to perform such measurements. And this is one of the first struggles we have actually at ISOL. And in facilities like ISOL, I'm thinking about Triumph in Canada, for instance, also where I'm working now actually at ISOL, where we're actually faced with this issue of having to find the ions that we want to measure among a zoo of other things that are being produced all at once, okay? Because even though we have mass separator, to perform a mass measurement in a panning trap, the mass separators are not, the dipole mass separators are not enough to give us only the ion that we want, okay? And thanks to our collaboration with a group in Greifswald, we have actually put in place this mass measurement method and separation, which is based on a multi-reflection time-of-flight mass separator device. And the idea of this device is quite simple. You take the beam from the ISOL facility, you inject it in a radio frequency cooler and buncher, and you get out of this, right? You transform a quasi-continuous beam into a bunch beam. And then you inject that beam, right? After a first energy reduction from 30 kilo electron volt to about 3.2, you inject that beam into this MRTOF device, right? And it's in a way an inverse beam shaker, right? You take this bunch of isobaric, which is not isobarically pure, right? You put it in the device, and because of the multi-reflection between the two mirrors, this beam is actually traveling around in a few tens of milliseconds, close to a kilometer, okay, within that cavity. And because of this distance, the different constituents that are initially composing this beam will naturally separate in time of flight, right? Coming out of the RFQ, they have the same kinetic energy, they have the same flight path. The only thing that are different to them is, in this case, is their mass. So the time of flight spectrum that we obtain on a time of flight detector, which is situating downstream of the MRTOF, is a well-separated time spectrum, such as the one which is shown here. And this is obviously not shown at random. This is a cadmium or A equal 131 spectrum, which was obtained in 2015 and which has been published by Dinko Atanasov and other collaborators in physical review letters, which shows the mass measurement of a very interesting isotope for our process calculation, which is 131 cadmium. Okay, so this technique is very interesting because we can get a resolving power of in excess of 10 to the 5 and more nowadays in only 10, 20 milliseconds. And we can actually not only use this as a mass separator, but also as a mass spectrometer. Obviously, for instance, in that case, the mass of 131 cesium is very well known. So we can use it to calibrate this time of flight spectrum and extract a mass value for an unknown species. And with this device, we can typically get a precision on the order of 10 to 20 keV, which is for most application in nuclear astrophysics is enough. Okay, so now it's nice. We have found ion of interest, right? In the case where the beam production is enough so that we can separate this ion of interest and send it to the panning trap, we cannot actually perform the actual measurement in the panning trap after a further cooling and a further preparation stage, which I won't detail here. But the idea here is to perform a high precision measurement. So if before we were in the 10 to the -6, 10 to the -7, I would say, relative precision range, now we are entering the realm of the 10 to the 9, 10 to the 8 relative precision range. And here I show a beautiful measurement of the mass of 130 cadmium, still from that same paper from 2015. And obviously, there's a few differences between the panning trap and the MRTOF. We are half-life limited. In this case, we have a much higher constraint on the number of particles per second that we need to perform the measurements. The resolving power is much higher, but as with any panning trap measurement technique, the mass resolving power can be large, but the excitation time, so the measurement time has to be long, right, to obtain such a high resolving power. However, if the half-life of the ions allow it, we can easily reach a precision of 0.1 to 10 keV with only 1 or 2 spectra, exactly like the one I'm showing here. The main disadvantage of that technique, it's actually a scanning technique. So here is represented the mean time of flight as a function of an excitation frequency, right? We probe the ions in a panning trap by exciting them with an RF frequency. And the problem is that to obtain each of these, here it says mean time of flight because each of these points is the mean time of flight of different scans at each of these frequencies. So we need to make the measurement here takes a long time, not only for the excitation, but also to obtain enough points and statistics to obtain such a curve. Okay, so So why are neutron-rich cadmium so interesting? Well, because actually of their relevance for the R process. Okay, so here is represented the R process, well, the nuclear chart and some R process abundances in different region. And this region south of tin 132 is very interesting because despite the difficulty of measuring nuclei in this region, actually some of them, including cadmium, should still be possible to attain at current nuclear physics facilities. Okay. So obviously, this is also related, and the interest in this region is not only motivated by our process, but also by strength and the evolution of the strength of the N=82 shell gap south of tin 132. So this is the beauty of this type of measurement with in mass measurement, is that with one, I would say observable, we can actually all at once study 1, 2, sometimes even 3, I would say physics cases all at once. So this is very, very nice. So for the measurement that I showed and I presented when I was mentioning the mass measurement technique, from this 2015 paper, the main goal was not only to assess the strength of the shell gap, which was shown to be drastically reduced actually, south of tin 132, but also to have a look at the impact on the abundance pattern obtained during in different scenarios for where the R process is thought to occur. Okay, so here is a few. Here is a I would say this is a zoomed out version of on the second R process abundance peak. And what is quite striking here, actually, so this is compared to the 2012 AME mass data evaluation. And what is quite striking here is the fact that with only at the time 3 measurements, so only adding these 3 measurements had a drastic impact on the calculation results of our process abundances. So this was quite, this is due to the fact that in that case, we found some 400 keV deviation. But it is quite interesting that only 3 masses, and this is really the message that we draw in that paper, that with only these 3 masses are impactful enough to produce some impact and guide further calculations. Well, obviously, we didn't want to stop there, so we revisited this region in 2017. And there, in this case, we really tried to focus on where we stopped before, right? In 2015, we stopped there at A=131, and I showed an MR-TOF spectra, which we obtained at the time. But we wanted really to go much further than that. And because the yields were on our side, I would say that time around, we managed to get a time of flight ion cyclotron resonance technique, so a penning trap measurement for this A=131 this time, which confirms the previous MR-TOF result from 2015, but improves the precision by a factor of 3. And one of the most actually thrilling measurement that I had the chance to participate in during my time at ISOL Trap, we managed actually to measure for the first time the mass of 132 cadmium. Okay, so this is an MR-TOF spectrum because this was one of the really most challenging measurements that we ever attempted at ISOL Trap. It's a really clean spectrum. It was unambiguously identified because we used laser ionization to go from the atomic cadmium to the ion. So we have a clear element selective on-off effect, I would say, by turning on and off the laser. So we know that this is cadmium and this is on the right mass. And this is a first time measurement. And this was published 2 years ago, also in Physical Review Letters. But what is the R process impact of that? Well, actually, that time around, we went to Almudena Arcones, and we asked her to perform measurement calculations for us. But she found that in this case, the R process simulation are not specifically sensitive to our new masses. And she pointed us, so here we represent the abundance in a zoomed out again region around these 2 the second R process peaks. So in black is the solar abundances, in blue the standard curve obtained from the latest AME calculations and previous measurements. And we are looking now at the sensitivity study, I would say, of the measured masses between the green and the yellow curve. And she was pointing at the importance of fission product recycling in this peak. So what do we get from that? I would say that, first of all, it sounds a bit contradictory in a way with what I was presenting on the previous case for the 2015 measurement. But what is interesting is that no matter what I would say we do here in terms of mass measurement, we always have and provide, I would say, guidance to this type of simulation, because we actually, well, need this data, high precision data, to be sure that such an effect is not just a spurious effect from simulations.
What was the trajectory for the alpha?
I have to check that. I can give you the. I think so. Okay. Yeah. So, and what about in that case the A below 130 case? Well, a few isomeric states were observed in 2013 in odd even cadmium isotopes, and we decided to actually revisit these as well, but this time using the most up-to-date, I would say, and performant mass measurement technique that is currently available for radioactive ion beam at radioactive ion beam facilities. And this is the so-called piicr technique, so a phase imaging technique, right, where we directly image I would say, well, it's a technique which is based on measuring the position and the trajectory of the ion in the trap directly onto a position sensitive detector, right? So we the first step of the measurement is to obtain a center of our figure, and in two other steps to obtain these two spots. And it's not complicated to understand that based on this figure, knowing the center, the position of one spot, the position of the other spot, and the angle between them, we can relate, right, these two spots to a either here in that case an excitation energy, but in the case of a regular mass measurement, we can perform with this a direct mass measurement. So this is what we obtained for that mass in 2015, and this is what we obtained in 2018, where now we have clearly two spots that are corresponding clearly to the difference in energy between the two isomeric states in 129 cadmium. So here we obtained in only 100 milliseconds a power in excess, resolving power in excess of 10 to the 6. It was the first measurement of the excited state of the excited energy in 129 cadmium, and based on, since the measurement were based at the same facility using the same production method, we can actually even obtain a spin assignment by comparing the results from the mass measurement in terms of the ratio of the isomeric to isomeric and ground state with respect to what is observed in the collapse measurement, which is a laser spectroscopy technique, right? And this is what we obtained. So it's represented here, the neutron number as a function of the energy difference between the two states. And what is quite interesting is to find that actually we observed for 121 cadmium a state inversion, meaning that the ground state becomes the excited states at 129. And why is that actually interesting or important? Well, if one looks or considers it in a simple, I would say, naive spatial model picture, one can compute from the one neutron separation energy between the Z equal 50 and the Z equal 49. Yes. chains, one can compute actually the separation energy, the neutron binding energy, right? So what is represented here is the difference between, let's say for Z equal 50, the difference between the mass of 132 tin to the mass of 131 tin, right? And based on this, we see that actually the state inversion shows a rupture of slope between the 3/2 states, so the curve that represents the 3/2 state and which represent the 11/2 states. And this slope actually is or should be related to the monopole part of the interaction. So this is also providing us some interesting results as the the behavior of the n equal AG2 shell gap going below actually Z equal 48 by extrapolation. Okay. And now we go completely on the other side. So now we are going on the completely other side of the nuclear chart. So, and this is what is also very beautiful with this technique, is the possibility to use this technique on, I would say, what in a previous presentation I called mass measurement at the extreme of the nuclear landscape, because it's really like pushing the measurement on one case to 132 cadmium, and on the other case, flip completely back and go to highly neutron deficient isotope and measuring things very close to tin 100. So here we are actually interested, or we were interested to measure these masses, which are reaching close to tin 100. And it's actually very similar to what has been showed in a way for cadmium, in the way we perform the measurement. And this is something which was absolutely beautiful, because in 3 days, we managed to measure these 3 isotopes using 3 different techniques. And this is something that we are very proud of, I would say. So obviously this will be used to study the evolution of, yeah, there's a typo there. No, obviously we want to study the evolution of a nuclear structure towards tin 100 here. So first, actually 101 indium, also all the odd even indium isotopes are exhibiting isomers, right? In the same fashion that the odd even cadmium isotopes were showing a low-lying isomeric state. So in 101 indium, we managed to perform for the first time a piicr separation, so a phase image separation for 101 indium. The idea again here is that we reach a resolving power in excess of 10 to the 6 in only a few tens to 100 milliseconds, right? With an uncertainty below 10 kilo electron volts, okay? What is important is that actually this was not the first measurement which was published, but there were 3 groups, us plus 2 other groups, which were interested in isotopes all at the same time. But the beauty of physics is such that all the measurements are agreeing with each other. We also managed to perform, for the first time, the mass measurement of 99 indium. This isotope is just 1 proton below tin 100. And we can see that we have a clear separation. So this is a time of flight measurement or a time of flight spectrum in the MR-TOF. I show the bin spectrum here with a reference ion, which is strontium fluoride. And here, the clear peak, which is unambiguously identified, again, thanks to a laser on-off effect, to 99 indium. So we know with the MR-TOF that what we have is A equal 99. And thanks to the lasers, we know that what comes out or comes in is indium. So there's no, I would say, debate possible on the nature of that peak. We managed to collect a few hundred ions. And as I said, this was the first measurement. We managed to perform 100 tin indium also measurement using the penning trap, right? And here we managed actually to reach a few keV precision, which is a factor 90 times more precise than any previous measurements. And this we managed to do in only two resonances, so two such files were taken. We performed the piicr study of this because we were worried that there would be in this spectrum maybe a state that we cannot resolve. So we performed a study using the piicr technique, and we found actually no long-lived isomers. So we are sure that this is a clean spectrum. And what is beautiful and interesting here is that this mass is actually linked directly to the mass of tin 100 through a beta decay Q value. Yeah, so these results are very important. First of all, because again, I would say doing the same and playing the same game as what I showed for cadmium isotopes, we can use these to study and look at the evolution of the Z equal 50 gap towards n equal 50. And this is a very important input for phenomenological shell model, because these states, especially at Z equals, well, these states at Z equal 49, at n equal 40, yes, Z equal, this state, sorry, at n equal 50 and Z equal 49 is actually directly an input of shell model calculations. So instead of measuring those single particle old states or extrapolating their binding energy through beta decay studies or other studies, now we have a direct measurement of their position with respect to the tin core. And obviously, we use this to also look closer to the physics of tin 100. So here I represent the two neutron empirical shell gaps. So this is directly extracted from the binding energy. This represents well, the strength of the shell gap at a magic neutron number. And here I represent this quantity. So in open, in empty, what do you call this? Yes, well, in empty points, yeah. Yeah, so as a function of a proton number. And one observes that at the crossing of a magic number, this quantity, the shell gap, is maximal, okay? But this is a quantity that we cannot use to study tin 100 at the moment because there's simply no data available to perform such a study. So what we did instead is play a trick, is compute the same quantity, but by shifting that quantity, the calculation of this quantity by two neutrons. And we see that everywhere we have a maximum for at a magic proton number, here we observe a minimum in the shifted quantity. And this shifted quantity here, which is represented in solid points, is actually something we can extract for the current data. Something we can extract from the knowledge of two beta Q value measurements between tin 100 and indium 100, and in red are measurements of 100 indium, 99 indium. Okay, and what do we learn from that? Well, we learned that if we look at separately, right, without doing the average at these 2 points, so in blue, the point which is extracted from the Lubos et al. Paper, which is the 2019 measurement reported for the Q value, and the older Inca et al. Paper in 2012, we see that actually this Lubos measurement seems to deviate from the trend which is initiated here in the shifted two neutron shell gap starting at n equal 44. So we see that all the way here within error, we are slowly going down. This is emphasized by our point at z equal 49, right? So it seems we are indeed approaching tin 100 as if we are approaching a magic number. But here, considering only the Lubos et al. Paper, we observe a deviation which is goes completely off the trend, and which is very actually hard to explain or interpret physically speaking. While the Lubos et al. Paper is actually within error compatible with a W magic tin 100, which is what is inferred from the trend. So this is, I would say, the further we can go at the moment with mass measurement without measuring directly the mass of tin 100. And obviously, we also use this to test ab initio theories, and especially pairing. So here I represent the pairing strength as a function of neutron number in different chains. indium tin chains. And these are very crucial because the approaching n equals z equals 50, the pairing between the protons and the neutrons are enhanced. And it is very important to test ab initio methods so that are calculating nuclear properties from first principle in this region, because the tin 100 region is highly used actually as a benchmark for such calculation. There are now readily available techniques that can target this region. And what is very interesting, and what I found beautiful here actually, is the fact that without any, I would say, constraint or experiment constraint on pairing, maybe not in magnitude, but at least the trends are reproduced fairly well. And there again, we see a discrepancy if we look at tin 100 between the Lubos et al. Measurement for the Q value and the Inca et al., where again, it seems that even in the pairing, it's hard to attribute, it seems, sorry, that the Inca et al. Paper is favored, okay? And it's even more pronounced in looking at the proton gap here. Okay. You good in time? 10? Perfect. And we did not stop there, because this region, also around tin 100, is quite important for our p-process calculation. And we asked Weijia Ong to perform, who was working with NIH Schatz at the time, to perform our p-process calculation and looked at the abundance of, the abundance in, how do you call this? The abundance, the fractional abundance in type 1 X-ray burst ashes. Okay, and here we see actually, so the fractional abundance as a function of neutron number, taking into account the ISOL Trap measurement and taking into account the ReactLib database. The difference doesn't seem to be much on that scale, but when we actually show the difference in percent, we showed that our masses actually can affect up to 55 to 60% these fractional abundances. So again, a few masses which have a strong impact on the results of astrophysical calculations. Again, we like not just to stay at what we measured, but we would like to always push further our measurements. And in 2021, we revisited this region because if 101 indium has an isomeric state, then 99 indium should have an isomeric state as well. And we decided to go and attempt to, for the first time, measure that isomeric state. But due to the rate, we could not do it in the pending trap this time using the piicr technique, but we managed to, in the weeks before the experiment, to really push forward the MRTOF mass measurement technique to such a degree that we could actually, and we can now actually at ISOL Trap perform isomeric state separation and measurement into with our MRTOF. So here is showed the 101 spectrum, where we clearly see the ground state and a shoulder, which is clearly visible, which corresponds to the isomeric state, right? Before, this could only be obtained at ISOL Trap using the piicr technique. And here I show the 99 indium spectrum, where we clearly see, again, the ground state peak, which is actually fitting with the measurement we obtained in we measured it in 2018, but was published in 2021. And here, some counts above background, which are actually corresponding to the isomeric state. So this is preliminary results. Lucas Nis is currently a PhD student at ISOL Trap, is currently finishing the draft of the paper, and this will be submitted very, very soon. But here is the first measurement of the excitation energy of the 99 indium isomer. To cross-check our measurement, obviously, we didn't stay there because all of the other isomers in the chain of indium are well known. So since it was the first time the technique was used, we really went through the whole chain in order to collect data. We even managed to measure in one indium to measure 3 isomeric states for one single nucleus. And we measured 11 ground states and 7 isomeric states for physics and systematic study. And this really was a beautiful mass measurement campaign as well. And now a few perspectives. I would say it's where scientific perspectives meet personal perspectives. Because this, what I presented here, up to here was things that I took part in with the team at ISOL Trap at CERN. And now I'd like to show a few highlights of the projects that are actually receive funding from the ERC and that are led by Professor Anu Kankainen at the University of Jyväskylä, which are dedicated to mass measurement for nuclear astrophysics. So what is actually the main difference between ISOL and ISOL? Well, first we take a primary beam, which comes from a cyclotron. Up to here, not much difference. The main difference being here that we actually use a primary beam to hit a very thin target, right? In our case, at ISOL, it's a thick cylinder about the size of my, how do you call this? Laser pointer here, right? At ISOL, it's a very thin target. The recoil ions, which are produced, are stopped in helium buffer gas, and then they are extracted using a supersonic jet guide. And a sextuple ion guide is used to guide the ions out of the target chamber. So this is a fast technique and chemically insensitive, whereas at ISOL we have high intensities of secondary beam produced, but we are limited by chemistry and slow release in our measurements. So, and different, what is very nice at ISOL is the fact that different geometries for this target chamber can be used to maximize, I would say, the extraction and the production of secondary recoil ions out of the target. So the target chamber is located here, right? And then we have then from there on, everything is very similar to ISOL, just as a much smaller scale. We have a dipole mass separation magnet, a switch yard, and then on a high voltage platform, an RFQ cooler buncher, now an MR-TOF, and a penning trap system as well. So there will be future campaigns which are actually received support by the ERC grant, and Anu's former and current postdocs are leading these projects. In this case, for instance, it's Antoine de Roubin, who is leading a project on mass measurements in the vicinity of 78 nickel for nuclear astrophysics, both to study the stellar abundances, right? Better constrain the theoretical models and understand, again, the residual solar abundances, and also perform, as I showed, it's always going hand in hand, I would say, do both at the same time nuclear structure studies and astrophysical studies. And again, here, the two tools that we will be using are penning trap, the piicr technique, and the newly commissioned MR-TOF. We have a student that did an amazing job, Ville Virtanen, who worked very hard to develop that MR-TOF for the ISOL hole. And we had a first run this year in October. And let's say we are still looking into the data and to see what we, not to see what we collected, but it was a difficult run due to, well, it's the joy of experimental physics, let's say. But we still collected data, and Ville is currently the student that developed this MR-TOF, is currently working on this. And we will have a second part next year, which is more dedicated to penning trap measurement. Also, something which is quite interesting at ISOL is the possibility to not only use, well, the regular gas cell, but also to use dedicated gas cells to, for instance, in this case, study multinuclear transfer reaction, okay? And this was an experiment that, the third stage of an experiment that actually ran last week, so I have nothing to show yet. because I left the experiment to come here. But the idea is to have here a dedicated gas cell, the geometry of which has been optimized in simulation, and a target wheel, right, where some thin foils would be inserted here. This is a demo, but usually you have a bismuth or yttrium or platinum foil, which are being put in these, I would say, donut-shaped empty spaces here, right? And use the cyclotrons to produce a 136 xenon beam to impinge on those rotating targets and to produce multinuclear transfer. This was tested already with 131 xenon and 209 bismuth targets. And here is a spectrum, an alpha spectrum that was obtained in about an hour of measurement. And we clearly see actually traces in parts per million of 2011 bismuth and 211 polonium isomeric state and ground state, which means that this technique is working. We can actually use this technique to produce radioactive beam, and we have extract them from our gas cell. And what was running actually last week, and there's again a typo here, it's not 138, it's 198 platinum. All of my apologies. What we tried this time around is to repeat this, of course, to make sure that our target were performing very well. But this time around to actually try to perform actual measurement of astrophysical relevance, meaning using a 198 platinum target and produce 198 iridium and 198 osmium. So on this nuclear chart here, it's a zoomed out inset. You have in black the stable nuclei, in red the 198 platinum target, and the red cross are, I would say, our objective, or were our objective during this run. And the color code, especially the purple isotopes here, are the ones that, in calculation performed by Manfred Manpower and his team, were shown to actually have the biggest impact on our process. So this is, I would say, more to come in future conferences, but this is a project which, again, is led by one of Anu Kankainen's postdoc, and that's Olga, sorry, Beluskina. So now for the conclusion, I think it's good. So summary, what about high precision mass measurements for nuclear astrophysics? Well, I hope I showed that it's key to guide nuclear astrophysical physical modeling, not only, I would say, to calculate abundances, but also not only in one, I would say, process like the R process, try to see what are differences between different R processes path or scenarios, but also between different types of, I would say, processes, RP process, R process, and other things. It is particularly challenging measurements because we have to reach in quite, I would say, the edge of what is currently possible at current radioactive ion beam facilities. But fortunately for us, ion manipulation techniques are becoming always more performance. And not only, and new projects and upgrades at existing facilities. So I mentioned the MNT project at ISOL, for instance, but also now the EPIC project, which is an upgrade project at ISOL, are there to try to push again the limits of what we can produce, and hopefully all together continue to produce a high quality of mass data for not only nuclear structure, but also for purpose of nuclear astrophysics. And with that, I would like to thank all my collaborators here, mostly the ISOL Trap collaborators, but also Anu Kankainen and all the ISOL team for their work. Thank you very much.
Okay, thanks a lot. There's a discussion at the end of the session, but we have maybe time for 1-2 questions. If anybody wants. Online, I have no idea how to see that. Okay, there's one.
So Indium 100 and 102 didn't have isomers. Are they expected to have isomers, or did you just not see them?
For indium, for the indiums. Where is that? 100?
Yeah,
102.
100 and 102.
Well, we don't see them in the production at ISOL. The production of, so we are lucky enough at ISOL to actually have the odd even isotopes that are being produced because they are low-lying states. And so we are lucky in the production method. For 100 and 102, as I said, for 100, we were expecting some isomeric states, but we didn't see it. So that points to rather the production mechanism, which is here to be responsible for this.
Okay, so you think it's production rather than something interesting happening with the.
Yeah.
Okay, anything else?
Yeah, it's a very nice question, but when you show the average time of flight in the solutions in the is this somehow a way to determine a kind of dispersion in near time of flight measurement in the end? So does it give you kind of uncertainty, or how do you?
So the red curve is actually yeah, that's the point. So the black points are representing for each frequency at which we excite the ions. This black point is the average and width of the time of flight distribution for that, I would say, frequency bin. And the red curve is a fit to theoretical data. Okay, so this is a so-called Ramsey resonance, but the center fringe here, the center frequency corresponds directly to the free cyclotron frequency of the ions. Okay, so from the fit, we extract the uncertainty on the mass data. If that answers the question. Right.
So it doesn't matter. So how large are these? Is these oscillations up there? I was just.
It does in a way. Just geometrically, I would say also for the more regular technique. This is so-called Ramsey technique with separated fields, but which are coherent in phase for the excitation. But if you were to increase, I would say this further, I would say the amplitude, you would probably get a better constraint on the mass, just geometrically speaking, because what is important is basically not not those points that are at the bottom here of the center fringe, but these ones that are actually constraining the fit towards the. Oh, wow! Sorry. Yeah, so it's perfect. Actually, it was the moment, right? It's the same for the more regular technique where you have one center fringe, looks like more, I would say, a diffraction pattern, the regular technique. And it's the same. It's really the points that are at this, on the edge of this minimum that really defines the position of the center. They have the most weight in the fit. So the precision is also due to, and this is due to tuning. So this is also our job as mass spectrometrists to make sure that we tune our setup in such a way that we get the best performances for it.
It's quick. So related to that, so do you have to do regular spacing, or can you focus more data points on those where you just?
Well, it's easier to do regular spacing, I would say. It's a very naive answer, but it's a very naive answer to a very good question. Yes. Actually, yes. I mean, there are some points here. All the points don't have the same weight in a time of flight measurement technique, whether it's Ramsey or especially in the more regular technique. So indeed, if you wanted to be more efficient, you would take less points away from the resonance position and more points on this edge. But this is a matter of, I would say, data acquisition programming rather than.
Okay, so now we would have Juliana's Stank queue. I have no